Welcome to the 6th lecture of combinatorics. So, we continue with the elementary concepts. In the last class, we were considering this problem, how many k element subsets are there for an n element set, right. Here the n element set, let us write as n equal to 1, 2, 3 up to n. And what we are interested in is the k subsets of it, k element subsets of it. I mean subsets which contains k elements out of these n elements. How many we can form? So, our method was to consider two sets. One set we are already familiar, namely the set of, this is called T, the set of all partial lists from this 1, 2, 3 up to n containing k elements. Means partial list means we want members of the list to come from this set. At the same time, the members should not repeat. For instance, 3 element list can be 1, 2, 3, 3, 2, 1 or 4, 3, 2 or 4, 3, 1, but never 4, 3, 3. Okay. So, we have already seen that we can get n k, this many number of, or it is also written as n p k, this many number of such things, right. So, that is, we saw that if you want to make a list of k elements, we can put the positions for the list k. The first position is this, second position is this, third position is this, fourth position is this, and this position can be filled by any of the n elements here in this 1, 2, 3 up to n. And this position, once you have used a member here from this thing, so we have only n minus 1 available things, and like that by the time you reach here we have only n minus k plus 1 available things. So, this number we have seen that this n p k is equal to n into n minus 1 into up to n minus k plus 1, right. And so, this many number of, that is n into n minus 1 into say n minus k plus 1 members are there in this thing. These are not points, these are, each of them is a list, right. Now, we say that we consider the thing we want to count, the set S. What is that? The k element subsets of n, subsets of n. And we told we will construct a function from T to S such that it is a, it's a so called D to 1 function where D is equal to k factorial. This is what our plan is. So, again we will draw a bigger figure. So, this is our T. Here we have this partial lists, right. So, this is, each list is written here, say. So, partial, so each list has k elements, it is taken from the n 1, 2, 3 up to n, right. The k lists formed from this thing. So, the number is n into n minus 1 into n minus k plus 1. This many are there in this thing, that is the cardinality of T. Now, our set S, this is the subsets which have k elements in it, which are formed from 1 to up to n. Now, give me one k element subset, any, maybe it is 2, 3, something, some members here, right, 2, 3 up to say 2, 3, 4, some k elements are here. So, for instance, we can take a value for k equal to 3. So, I will take 2, 3, 4, right, as a subset of 1, 2, 3 up to n. Now, from this thing, the function is constructed like this. If I see a list here, say 1, 2, 3, I will map it to the set 1, 2, 3. So, this is different for this is a list, but this is a subset 1 2 3. Here there is no order. So, the mapping comes like this, this is mapped to this thing. And also note that 2 3 1, this is another member here, that also will get mapped to this, because that is underlying set of members are 1 2 3 again. So, on the other hand, this 4 5 6 is a list here, this will map to another set, say 4 5 6, right. Say for instance 6 4 5 will also map to this, right. Now, you see that this is indeed a function, because each list gets mapped to a specific member here. It does not get two different choices. It is clear that the elements which are present there only, that set only it gets mapped, and it is a k element set, right, because the k list k element, nothing is repeated here, there are indeed k things here. Now, of course, many things are getting mapped to this. The question is how many things will get mapped to the same thing. For instance, this 1 2 3, how many things on the T side, lists on the T side will get mapped to it. Of course, all the lists which can be formed using this 1 2 and 3 will get mapped to this, right. There are 6 of them. How did we get it? We just arrange all the 3 factorial, consider all the 3 factorial lists we can, so permutations of 1 2 and 3, those things will get mapped to this only and only to this, right. And we can say that every 3 elements set here will get map, will have a pre-image. So, he will have 6 pre-images, right. So, just so therefore, it is a k to 1 function, right. D is equal to k here. So, therefore, here we can see that for each subset, this is a subset of cardinality k. So, this is right, these things are getting mapped to this, the lists are the k factorial of them will get mapped, because this is a k element subset, k factorial permutations are there for the members here, right. Each of those k factorial lists will get mapped to it, nothing else will get mapped to it, and each of these things will get mapped to this only. So, this is such a function, and by our division principle, now we can say that the cardinality of this set S, right, the cardinality of S is equal to cardinality of T divided by k factorial, and we know the cardinality of T. What is that? This is the all possible k lists, partial lists, that we can form using the members of 1 2 3 up to n without any of them repeating, that is n k divided by k factorial, that is n into n minus 1 into n minus k plus 1 divided by k factorial, right. So, this is exactly the number of subsets that we can form out of the members of 1 2 3 up to n, and which consists of only k elements, the cardinality k subsets, right. And this number is written like this, n c k, or another notation is n c k. This is the most important number in combinatorics, of case n c k, right. So, we can easily see that n c 0 is equal to 1. Why is it so? Because the 0 element subsets are only 1. So, that so because we have to also write, so note that n c n equal to 1, right, because only one subset can be formed out of n element set, right. For note that I think when we define permutations, we should have told that 0 factorial is by definition 1, though it does not make sense, because what, so usually we write n factorial is equal to n into n minus 1 into up to 1, right. So, when what do you mean by 0 factorial? You just say that we define it like that to make things convenient. So this is for all values of n greater than equal to 1, this will make sense, this definition will make sense. So then if you wanted to derive this NC0 using the method earlier, so what is the number of 0 element lists from n element set? We should just say it is 1. So I don't know, it's by definition, or otherwise we should take it separately. So NC0 is equal to 1 because 0 element set we know that it's empty set. The earlier method is telling us that so here we will list all the k partial lists. So there are 0 partial lists, right? So that's an empty list. So it doesn't really make sense there. So we don't have to rely on that proof here. So we can just note that NC0 is equal to 1 because we have an empty subset, right? So that's a 0 cardinality subset from this thing. So NCN is the full subsets. This definitely makes sense because n factorial pi n factorial is what that formula gives, that gives us 1. So for all other things we don't have any problem. So we can easily note that NC1 is equal to that n into n minus 1 plus 1 is n, right, divided by 1 factorial. So this is n. So this is also easy to see how many one element subsets are there, that means how many singleton subsets are there for n. So that is definitely subsets 1, 2 up to n, right. Now how many, so what is n choose 2? N choose 2 is n into n minus 1, that is the upper term, 2 factorial is 2, n into n minus 1 by 2, right. So this is also easy to see, it's just a way of picking up 2 elements from n things. So for instance we can ask, so given a graph on n vertices, and we are considering simple graphs, no multi edges, no self loops. Now suppose it's a complete graph. Complete graph means all pairs are connected by some edge. I mean, if there are 2 different vertices, there is an edge between them, right. This is the kind of complete graph we drew. Right, and then yeah, this I think I have drawn everything. So all possible edges are there, that means if 2 vertices are there, right, which are distinct, then we put an edge between them. So how many edges can be there in this graph? This is the complete graph on n vertices. How many edges? This is also denoted by kn. So this is n choose 2 because we can just count it by asking how many pairs are there, how many 2 element subsets of vertices are there here. There are n vertices, the number of 2 element subsets are n choose 2, that is n into n minus 1 by 2, right. So you can count it in different ways also, but just to illustrate one of these places where NC2 comes, n choose 2 comes, right. So that is about NC2. Now we mention one important theorem called binomial theorem. This is mentioned like this. So x plus y raised to n, here n we are considering as a positive integer, so is equal to n choose 0 into x raised to 0 into y raised to n plus then n choose 1 into x raised to 1 into y raised to n minus 1 plus n choose 2 into x raised to 2 into y raised to n minus 2 and plus and so on till n choose a typical term will be n choose I into x raised to I into y raised to n minus I plus last term will be n choose n into this will be x raised to n and y raised to 0. This is the binomial theorem. So, here this is a formula which involves this combinatorial coefficients and NC0, NC1, NC2, etc. So, how do we derive this thing? So, this is easy to see. See, x plus y raised to n is actually what? That is x plus y into x plus y into x plus y, like that, n times, right? X plus y. This is coming n times here. That's what, right? Now, of course, so we want to expand this thing. What all kinds of terms will come? For instance, we can take a small example, n equal to 2. So, x plus y square will be equal to x plus y into x plus y. So, we multiply this thing x square. So, this is x square into y raised to 0. Say for instance, if I just say what power of each term we will write in terms of both x and y. When y is not there, it is y raised to 0, that is 1. So, this is x square. So, this corresponds to x y, this corresponds to y x. Y x and x y are same because we are think it's commutative of cases, x y and y x should be considered same. So, plus y square. So, this will make 2 x y, right. This is the way we write. So, this is we have x square y square y raised to 0, which is essentially only once, that is we can see that is 2 choose 0 plus, and then next is x y, that is 2 times, that's 2 times, that is 2 choose 1, 2 times is 2 choose 1 plus, then next is x raised to 0 y square, that is again 2 choose 2. Okay, so I should have written the other way, because this is the way I put it, 2 choose 2 here, because this corresponds to this, and this corresponds to the power of x here, and this corresponds to the, sorry, this should be 0, this corresponds to the power of x here, right. So, similarly, so let us say x plus y whole cube, right. This is equal to x plus y into x plus y into x plus y, right. So, now this is, see for instance, you can consider the first term as x raised to 0 term. That means all this we can take one y from here, because for every term here, so this x plus y term will contribute to the product, right. So, here it is y I can take, and here also I can take y, here also I can take y. So, that will make x raised to 0, because I am not taking x anywhere. So, that is x raised to 0 into y cube. So, you know what is so now the question is somewhere, for if I start expanding like this, will this term repeat again? We can see that it will not repeat again, because this y has come from here, y has come from here, y has come from here. For y cube to come, there is no other way, y has to be contributed from each of these gates, then only we can get this y cube, x raised to 0 y cube. So, therefore, it will come only one way. So, therefore, that corresponds to yeah. So, for instance, in another way what we can say is, see x should be contributed by none here, right. So, that means how many of these things, say this is the first term here, first term, this is the second term here, this one, this is the third term here, right. Out of these 3 terms, how many terms contributed x? 0 terms contributed. How can you pick up 0 number of terms from 3 possible terms? That is 3 choose 0. That is 3 choose 0, that is 1, only one possibility. That is what. And now the next thing we consider is when x is 1, so then y has to be 2, right? Why is it? Because I can take x from here, then here and here I can take a y, x into y, that will make a x y square. But then this term x raised to 1 into y square can come in different ways. For instance, I could have decided to take x from here and y from here and here. So, y x y, that would also have given this term. Another way of taking getting this term is to pick x from here, and I could have taken a y from here and here, that is y square into x, same thing. 3 different ways of doing it. Why? Because x could be selected out of these 3 different terms, which term can contribute this x raised to 1. So, there I can pick up any one out of these 3 terms to contribute this x. So, that is 3 choose 1, right. The 3 choose 1 into x raised to 1 into x square, right. Similarly, if I am looking for an x square, then the rest should be y. Why is it so? Because the total, see, x will come from 2 of these 3 terms, and the remaining term, that means third term, has to contribute y, that is x square plus y, because this some terms contribute x, some terms contribute y. Each term has to contribute either x or y and never both. So, therefore, the total contribution has to be the number of terms. Here it is 3. So, 3 2 plus 1 here, right. And the question is, which all terms are contributing x? 2 terms have to contribute x. How do we select those 2 terms from the possible 3 terms? 3 choose 2 is the number of possible ways. You could take either this 2 to contribute x and this to contribute y, the first 2 to contribute x and the third to contribute y, or you could select these 2, this and this, to contribute x and this to contribute y, or you could have selected this and this to contribute x and this to contribute y, right. There are 3 choose 2 is equal to 3 possible ways. And now similarly, there is yeah. So, finally we can see the last term, that is x cube term, right, x cube y raised to 0. That can only be selected in one way, because each of these terms have to contribute x, 3 terms out of 3, right, that is 3 choose 3. So, 3 choose 3 into x cube into y square. This is the way it is expanded. So, this is, I just took a small example to illustrate the point, right. Now, I can go to the general case which we wrote earlier, namely this one, there are x plus y raised to n equal to this thing, right. Now, how will I find out the answer? So, of case, so this is a general term, x plus y raised to n equal to x plus y into x plus y into, so n times it will come x plus y, this is total n times. Now, what all possible terms can be there is the first question. I will arrange it like this. There we can have say x raised to 0, y raised to n, because see, each term has to contribute either an x or a y to the product when you expand it, of course. And if no term is contributing x, then only x raised to 0 will come, right. It's contributing x to this. So, I am thinking of forming a particular term x raised to 0. So, every term has to contribute y. So, therefore, y raised to n will come, right. Now, suppose one of these things contribute x and the remaining things contribute y. This is this kind of terms. Now, this is 2 of these things contribute x and the remaining things contribute y. This is this kind of things, x square y raised to n minus 2 and so on, right. and in general see, suppose I of the terms contribute x and n minus I of the terms contribute, remaining n minus I terms contribute y. So, this is this kind of terms, and finally, we have all the terms contribute x, that is x raised to n, y raised to 0, this kind of. The thing is, several terms can be formed of certain forms, but you look at this one, this term comes only once, because x is contributed by no term. That can happen only in one way, because no terms, everything is y. So, right. So, that is only one. So, that we capture by saying that it is n choose 0, right. So, x is contributed by 0 terms, this 0 correspond to this one. Now, here x is contributed by exactly one term in this, and all other terms are contributing y. So, this will out of the n term, one term is contributing x. So, this one correspond to this. You know, when you take the product, it will be like x into y into y into y into like that, that is such a term. So, now y into x into y into y into y into such another term will become. So, then here y into x into y into such a term will come. So, we have to add them all together. So, just that we count, and that count is put as the coefficient, how many times that x raised to 1 into y raised to n. So, that is only we are doing, that is n choose 1. Similarly, here because the question is x square and the remaining are. So, the which two terms will contribute x square is the question. Out of the n possible terms here, we take 2 and we say that those two are contributing x square, these two correspond to this, right, and then the remaining terms are contributing. It can be these two terms, right, or it can be this term and some term here, right, any two terms. Those two terms are contributing x. In general, I terms are contributing x. So, that is n choose I, right, into x raised to I into y raised to n minus I, right. So, here for n choose n, because all the n terms are contributing n. So, this is what. So, this I correspond to this, right. So, this is the binomial theorem formula. So, you see here we have crucially used this notion of n choose I. What is n choose I? We are saying that here instead of, we always were saying that n element set, which are the n element set. So, this is the first term, second term. So, this is the way we consider third, nth term. That way we are saying that this is 1, this is second, this is third, this is fourth, though it is all written x plus y, but in this order we see that these are different objects, right. This is the first object, second object, this is the first object, this is the second object, this is the third object, and this is the nth object, like that, right. And in that sense we can say that we are selecting which objects correspond to this I x raised to I. That means those x's, I x's are coming from which objects. That means we are selecting the I objects out of n objects, right, just to get this x raised to I, because once you select the objects which give x, the remaining things will automatically give y. That is why x raised to I always comes in x raised to I into y raised to n minus I. It is not possible that x raised to I into another power of y comes, right, because the remaining all terms has to contribute to y. So, therefore, and then when we add up to see the coefficient of that, we have to see how many times that has occurred, that correspond to how many ways we can take an I set out of an element set. That is the point, right. So, therefore, this binomial theorem make use of this combinatorial coefficient. It is written in terms of combinatorial coefficients, and now once we talk about binomial theorem, so it also gives us some, because this in this equation x and y are variables, we can put some values for this thing, right. This is the way we wrote, and choose 0 into x raised to 0 plus y raised to 0, y raised to n plus, right, n choose I into x raised to I, y raised to n minus I, and finally n choose n x raised to n, y raised to 0. if you want a more compact way of representing this, so writing like this, you can write like this. So, I equal to 0 to n, n choose I x raised to I into y raised to n minus I, this way. This is what we first wrote, right. So, now we see we can try substituting some values for x and y. So, what if I put x equal to 1 and y equal to 1. So, what if I put x equal to 1 and y equal to 1, what will happen, right. So, then this will become this will become 2 to the power n, because x plus y 1 plus 1 is equal to, and what will this become? Here you put x equal to 1, y equal to 1, this will become 1, this will become 1, and here each term like this will become 1, because x raised to I is now 1 raised to I, that is 1 only, y raised to means 1 raised to n minus I is again 1. So, all of them are 1s, right. Now, this will become just this, right. So, we get 2 raised to n is equal to n choose 0, because that x and y's have disappeared now, n choose 1 plus n choose n. So, or in short form we can write 2 raised to n equal to sigma I equal to 0 to n choose I, right. This is, we got a relation between the summing up the combinatorial coefficients, where fixing I and so fixing n and varying I from 0 to n. This will give us 2 raised to n is what it says. So, the way we can interpret it is that the number of subsets of n, number of subsets of n is 2 raised to n. How do we see that? Because what is this n choose 0? This is the empty, the counts the empty subsets, counts the number of subsets of n with 0 elements. So, n choose 1, as we already mentioned, it counts the singleton sets, that means the number of subsets of n with just one element. Similarly, n choose I counts the number of subsets with exactly I elements in it. So, now if you sum up all these things up to n, we are actually counting all the possible sets, because any subset has to be has to have either 0 element or 1 element or 2 element or n element, right. So, therefore, this number is the total number of subsets of an n element set, and we are seeing that that is 2 raised to n by binomial theorem, right. Binomial theorem says that, right. We can again discuss this thing later, because different proofs, different comparisons, different strategies we can see. So, I think we already discussed it once, this number of subsets. It is a very basic thing, therefore, it will keep coming again and again. So, now so coming back to the binomial theorem, namely x plus y raised to n is equal to sigma I equal to 0 to n choose I. This was the binomial theorem, sorry, x raised to I into y raised to n minus I. Now, we can think of putting x equal to 1, say assigning x equal to 1 and y equal to minus 1, what will happen? So, then this will become 0 raised to n, which is 0, right here, because 1 minus 1 is 0. That will become I equal to 0 to n choose I, but here what will happen? Because whenever we have initially this I equal to 0 case, here we are getting, yeah, because we start with this thing, for convenience let us take this as minus 1 and this as plus 1. So, therefore, here we can, because this will not contribute any, because plus y is plus 1 raised to this thing will remain as 1, right, always this will be 1, but this case, so x raised to I, that will become minus 1 raised to I, right, this will become. So, therefore, this will be written as I equal to 0 to n choose I into minus 1 raised to I. This is what we will get. So, if you write it in detail, we are getting 0 equal to n choose 0 into minus 1 raised to 0 plus n choose 1 into minus 1 raised to 1 plus, so finally n choose I into minus 1 raised to I plus n choose n into minus 1 raised to n, right. So, this is what does it mean? But this, if you look at this stuff, this is just 1, right, we can just delete it. So, that is just 1. On the other hand, this thing is minus 1 raised to 1, we can't delete it, but we can rather remove it from here and make this a minus here, minus 1 raised to n is minus 1. And similarly here, this depending on whether it is even number of number or this thing for number or odd number, we can have plus or minus sign. So, this will be n choose 2 here, the next will be n choose 3 and so on until we reach here, we do not know whether it is odd or even. If it was even, this number we can remove this thing and put it plus only here, this can be, this will remain plus only. But if it is odd, if I is odd, then we will remove this thing and we can put minus here like that, right. So, therefore, we will get something like this. So, we can say that because this is 0, all the negative terms can be taken to this side. So, negative terms are those n choose i's where I is odd, right. Negative terms corresponds to those n choose i's where i's are odd. Therefore, what we get is something like this, n choose 0 plus n choose 2, that is even numbers I am collecting, these are all positive signs, n choose 4 plus like this. So, and then this will be equal to n choose 1 plus n choose 3 plus. So, the odd where this the i's are odd things, we can take it to the one side, whenever i's are even things, we can, they are going to be equal. Oh, in the terms of subsets, what we are saying is this counts the number of subsets whose cardinality is even cardinality subsets, right, this one, and this counts the number of subsets of odd cardinality, right. So, we are saying that they are same, right, the number is same. And again we can see other fancy relations also coming out of this binomial theorem. For instance, x plus y raised to n equal to, yeah, this was the formula, right, n choose I x raised to I into y raised to n minus I, where I is going from 0 to n. So, what can happen if I put x equal to 2 and y equal to 1. So, what can happen? So, these terms will go away then, because y raised to n minus 1 is 1 raised to n minus, sorry, y raised to n minus I, that is 1 raised to n minus I, always this will be 1. So, this will not be there. So, then it will be totally like this. So, this will go away, and here this x raised to x will be 2, right. So, it will become 2 raised to I, 2 raised to I. So, this will become something like this. If I put it here, this will be 3, because 2 plus 1 is 3, 3 raised to n here, 3 raised to n is equal to I equal to 0 to n, n choose I into 2 raised to I, that is something like this, n choose 0 into 2 raised to 0 plus n choose 1 into 2 raised to 1 and so on up to n choose n into 2 raised to n. Interesting. If you add up these things, so you should get 3 raised to n is what it says, right. So, we can produce such interesting equalities here using this binomial coefficient. It may come very useful sometimes. So, we will move on to the next topic, next idea. So, which is, so we have to, this is a very important thing, we have to remember that. The next notion, for instance, coming to the combinatorics. So, one of the main things is to count how many are there, how many objects of certain type are there. So, there are several techniques we use to do these things. So, what we have learned up to now is some elementary ideas. So, initially we were discussing about several principles like addition principle, when we know that two disjoint sets are involved in the whole, and then each separate set we can count, and then to get the total we just have to add. Similarly, when we know the whole, the total, and we know the size of the cardinality of a subset of it, then we can see the difference by see the number of elements which belongs to that big set and number of elements does not belong to the small set which is included in it, is given by subtracting the cardinality of the big sets, subtracting from the cardinality of the big set the cardinality of the small set. Like that, this was the subtraction principle. The multiplication principle was actually counting the number of members in the Cartesian product of two sets, right. When certain objects have several components and one component comes from one set and whose cardinality we know, and the second component comes from another set and so on, then we can multiply the cardinality of the individual sets to see how many are there. And we also discussed the division principle, and we were using the division principle to show the circular arrangements and then even to derive the n-choose, the number of subsets from the number of partial lists consisting of k things taken from n things, right. So, now we are talking about a certain general strategy here. So, this finally when we discuss the division the division principle, right, we told what we are thinking is like we have a set and T, and we have a set S, and there is a D to 1 function from T to S, in the sense that every member of in S, every element in S has D pre-images in T, and they are all definitely they have to be distinct pre-images, because this is a function. So, every member of T will get only one image in S, but then S can get several pre-images, but then they get exactly D pre-images. But then we saw that if you want to count S, one way is to count T and divide by T, right. So, like for instance, initially we considered the example of families, several families coming to a party, and each family has 2 children. If you count the number of children, then we can get the number of families also by just dividing by the by 2, right, because each family has 2 children, right. So, then here is a very special case of this D to 1 function case, namely when D equal to 1, right, T and S. So, that means here, so this is a function, but we know that every member of S has exactly one pre-image, that means D equal to 1 case. So, this is called a one-to-one function. D equal to D to 1 function is one-to-one function now, and this another name is bijection, right. So, you should revise what the chapter on functions and relations, and then recall what was bijection, surjection, injection and things like that. I will not get into the details of those. Bijection is the name for one-to-one function, but this is probably the time to just recall the definitions of like on-to functions, in-to functions, surjection, the different means of surjection, injection and things like that. So, this bijection is a one-to-one map. So, every member of T is mapped to this thing, but of course, something here, exactly one thing here, and every member of S is mapped back. That means the pre-image of it is a unique one. There is only one. There is one and there is only one. That is then we say that between T and S there is a bijection. So, this is the picture. So, you remember there won't be anything, any stray thing here sitting here without getting a pre-image, right, and also there won't be anything which will have something like this. That means there won't be any guy who has 2 pre-images. This is also not there, right. This is exactly like this in the graph theory, like, so it will, for instance, if you imagine this is a bipartite graph and this T is one side of the bipartition and S is another side of the bipartition, and this is a collection of, these are considered as edges, right, and this is usually called a matching, perfect matching, because everything here is matched and everything here is matched, and then that's a exact one-to-one mapping here, right. So if you are familiar with graph theory, otherwise you can forget about it. So so now this is a bijection. Now we see by the division principle we have already observed that if we to count this thing, we can just count this, right, and then say that T equal to S, right, because there is no division now, or whichever is easier to count. Once we establish a bijection, whichever is easier to count we count, and then we say that the other also has the same number of elements, right. So sometimes it can be easy to do, certain things can be easy to do, while certain other things need not be. Once we see a bijection, we see that okay, this is the same thing, so the number of things should be the same. That is the plan. So the simplest example, again we come back to counting the how many subsets are there for an n element set. This is what we were always saying, how many subsets are there for an n element set. So we had seen one strategy now, like we saw that it is n choose 0 plus n choose 1 plus n choose 2 plus, so n choose n. This is because this n choose k means we are counting k element subsets, that's the meaning of that n choose k, that's the way it is defined, and then we are summing up all these things, we are actually getting the number of subsets. And we have seen by binomial theorem that this is actually 2 raised to n, because this will be the expansion of 1 plus 1 raised to n is 2 raised to n, right. Now we try another method, right. We will do is to establish a bijection between a subset of the n element set. So subsets of this, right, n equal to 1, 2, 3 up to n. Take any subset of this, we will put a bijection to the binary strings of length, n. So this will be our T, right, the set of binary strings of length n, and S will be the subsets of this one n, right. We will now establish some bijection f between S and T, right. This is our plan is. How do we do this? So first we note that you consider some subset A from S, right. That means something like 1, 10, 3, 4 say. Now I say that looking at this subset, I can devise a binary string in the following way. Binary string I will write like this is the binary string I am going to write. This is the first position, second position, third position, fourth position, and this is the nth position. Now I will see 1 here, so I will put 1 here in the first position. Now I will look for 2 is not here, so I will put here 0, that means 2 is not on. I will look 3, is 3 present here? Yes, 3 is present, so I will put 1 here. Is 4 present here? Yes, I will put 1 here. Then 5 is not present here, I put 0. 6 is not present here, that I will put 0. Then 7 is not present here, I will put 0. 8, 0, 9, 0, and when I come to 10, I will see this here, I will put 1, and later I will put only zeros, right, because like this, because they are not going to be here. So I say that I am defining the bijection like this. Given this A, my f of A, that function value is this string, right. So, like that you can see that given any subset, I can define a string like this by putting ones at exactly those positions where those numbers are the members of this subset, and putting zeros for those positions where the position numbers are not in this subset. Now, you can see that given a subset, we can only define one such string, because it is exactly defining what the string is, right, because the positions where one is to be put, that the positions to be set are defined by the members of this set. So, and everything will get a string. So, this is indeed a function. Now, the reverse way, we can look at any string, and from this string we can read out see where in which all positions 1 has appeared. So, here third position there is a 1. So, I will make a subset like this, I will write 3, and then I look for 4, 5, 6, 7, 7th position there is a 1. So, I will write 7, and then say 8, 9, 10, 11, 11th position there is again a 1, I will write. The position numbers where I see a 1, I will collect, and that becomes my subset. That is the reverse. You can see that there is only one way of getting it back, and this is in the function. If I apply the function on this thing, exactly this string should come, right. So, this is indeed a bijection. So, when we say a bijection, we have to verify that what we are defining is indeed a function, and then from the other side we have to make sure that every member there is indeed getting a preimage, indeed has a preimage. Here, for instance, you take any binary string, you can create a preimage for it, you can see a preimage for that. And also then we have to say that no two different objects will get the same preimage. That means, for instance, if I take two different binary strings, it cannot get the same subset back, because the position numbers where it is set 1 is unique, right. Two different strings cannot have the same position numbers where the ones are set, and right, because so if you collect all the positions where we have put 1, that will give exactly one set here, right. So, two different strings cannot, unless they are the same string, cannot get the same set back. So, therefore, that uniqueness should be checked. This is what we have to verify when we prove that something is a bijection. This there is only one, there is a preimage and there is only one preimage for it. Sorry, there is a preimage, and then sorry, I think I made a mistake here. I am saying that two subsets, we just have to verify that two subsets cannot map to the same element. That means, given one member, you do not get two different preimages. So, the other thing comes on the function side. To check that it is a function, we have to say that everything every subset here is indeed getting a binary string. That means, it has to get a value. And second thing is two different given one subset, you should not be able to map it to two different things. It should be unique mapping, that is it, right. So, this will establish the bijection, right. So, this is one way of counting. Here what have we achieved? So, then we have achieved that so S is the number of so S is the subsets, and from that I have defined this bijection as I have described to the T, where T is the set of all binary strings of length n. Now, to count S, we can just count a T, because if we saw that this counting S, we required this binomial theorem and all. Now, we do not require binomial theorem, because we rather count T, right. We rather count the number of binary strings of length n, and how many number of binary strings can be there. Here we can use the product rule, because see there is n positions, the first position, second position, third position, n position. First position we have how many choices? There are only two choices, it can be either 0 or 1, right. The cardinality of these choices is, the set of choices is 2. Here also the same situation, 2 choices, 2 choices, 2 choices. So, now we can apply the product rule and multiply it out, 2 into 2 into 2 into, that will become 2 to the power n, right. So, therefore, there are 2 to the power n the cardinality of t equal to 2 to the power n, right, and therefore, the number of subsets is equal to 2 to the power n. So, essentially this choices here 0 or 1, understand that what when we put 0 we mean that we are not including it in the subset. This one, this position number, whatever the element corresponding to the position number is not being included in the subset. Otherwise, if you are putting 1 here, then that means this element is being included in the subset, right. So, therefore, it is a question of whether we want to include an element in the subset or not include in this. These are the choices. So, that is why when we want to count the number of subsets, so this choices for each element there is the choice whether we should include it in the subset or not include. So, that makes 2 raised to n possibilities, right. So, but from this bijection it should be clear how the counting is done. The next one is so another example for this bijection based proof is this one. So, for any positive integer n, the number of divisors of n that are larger than root n is equal to the number of divisors of n that are smaller than root n. So, what do we mean by this thing? So, you take say a positive integer 10. 10 does not have it is not a perfect square, but what is root 10? Root 10 is something like 3 point something, some 3 plus epsilon, say I do not know what exactly it is, 3 point something, right. So, I am interested in the divisors of 10 which are below root 10. So, that means up to 3. So, 1 is a divisor, 2 is a divisor, and then I am interested in the divisors of 10 which are above root 10, that is 5, because above 3 plus epsilon, above 4 or more, it is 5 and 10. So, it so happens that this number of divisors here is above root 10, this 2 here, and this is also 2. So, these are equal. We are claiming that for every number n it is like that. So, for another example we can take say 36 root is 6. The number of divisors of 36 which are below 6 are 1, 2, 3 and 4 divisors, because 1 divides, 2 divides, 3 divides, 4 divides, 5 does not divide, and the number of divisors of 36 which are above 6 is 36, 12, 18 and 9, sorry 18 and 6, sorry not 18, 36, this is 12, 18, yeah sorry 36, 12, 18 and 6, right. There are 4 here, there are 4 here. How come it is happening? Below root n the number of divisors is same as the number of divisors above root n. So, we want to show that these numbers are same. We will again use our bijective proof method to show this thing in the next class. Thank you.